In the previous section, we described the LabVIEW FPGA architecture on Windows and LabVIEW FPGA architecture with LabVIEW Realtime. By the end of this module, you will be able to describe common reconfigurable I/O platforms. Here we see common reconfigurable I/O platforms. So one is PCI and PCI Express if you want to put an FPGA board into a computer with PCI slots. Also, there's PXI and PXI Express if you want to put an FPGA board into a PXI system. And also there is CompactRIO. Here we see the R-Series multifunction RIO board. So this board comes in a PCI, PCI Express, PXI, or PXI Express form factor. You can use this to define custom data acquisition, and it's a multifunction board, so it has analog inputs, analog outputs, and also digital I/O. Also, it has a high channel count. Here we see a CompactRIO system. So first thing you can select is the reconfigurable chassis. So this chassis is going to be the component that contains the FPGA, and then you can also select the real-time controller. This is going to be where your real-time OS runs, and depending on what kind of controller you want, you can select the processor speed and the flash memory size. Also, you want to select the I/O and connectivity. So if we look back on this graphic, you see how there's different modules in there, and each module you would select based on the I/O that you need, whether you need temperature, whether you need digital I/O, whether you need analog input, and things like that. Here we see some other CompactRIO form factors. So the one on top, we see an NI CompactRIO integrated controller. In this case, the controller is connected automatically to the FPGA. So the FPGA and controller are one piece. Another thing we see here is a NI single board RIO. In this case, this is essentially the same thing as a CompactRIO, except it doesn't have the enclosure, and you can get it in a board format. Here we discuss FPGA size. So historically, FPGA size was measured by gate count. So here you would just say, well, whichever FPGA has the bigger gate count, that's the one with more resources and that has higher performance. However, now FPGA logic blocks and resources differ, so logic capacity and performance comparisons are tricky. So for example, now FPGAs might have specialized blocks. So some might have more multipliers, some might have more block RAM, and things like that. So it's not a straight comparison anymore. Also, the logic blocks might differ in capabilities. So one FPGA might use 4 input lookup tables, and the other one actually uses 6 input lookup tables, which can do more. So it's difficult to kind of just look at one spec and look at the gate count, and having that determine how powerful an FPGA is. Another thing is, it's difficult to map LabVIEW VIs into FPGA resources. So it's difficult to just look at your LabVIEW FPGA VI block diagram and know exactly how many resources it's going to need on the FPGA. What happens is the Xilinx compiler actually takes a look at the converted LabVIEW code, and it optimizes code based on the FPGA architecture. It maps things out to specific FPGAs. One thing you can do is you can verify that your FPGA code fits by compiling for offline hardware targets. So for example, if you don't have your FPGA hardware quite yet, in LabVIEW FPGA you can simulate that hardware and then try to compile your FPGA VI to see if it's going to fit. Another thing you can do is, instead of waiting for something to compile, you can also do a resource estimation, and we'll talk about that in a later lesson. So here we see an FPGA resource table. So because it's difficult just to compare the gates, what we have in this table is you see there is a row for equivalent logic cells. So here we try to kind of give a good comparison on the equivalent number of logic cells for each of those FPGA chips. So if you look at that top row, those are different example Xilinx FPGA chips. So here we see on this particular slide that the Vertex 5 LX110 has the most equivalent logic cells. Also, we see the number of resources for different things on that FPGA chip. So if you look on the left, you also see the number of lookup tables or flip-flops. You also see the number of multipliers on each FPGA chip, also the amount of block RAM, and in the last column you see sample NI products. So each of those NI products, it's mapping out which NI products use which Xilinx FPGA chips. So this is a lot of information. If you want more details on this, refer to the link that is shown on this slide for more information. So at this point, if you're able to, it would be helpful to do exercise 2.1. In exercise 2.1, you set up your CompactRIO system, and you're able to connect and power it up, and you can verify the proper connections. So if you have the hardware that's necessary to do this exercise, go ahead and do it now. So in this slide, we have a few discussion questions. So if you need to swap modules, do you first need to power off the CompactRIO system? With CompactRIO, the modules are hot swappable. So even if the CompactRIO system is on, you can feel free to take out modules and swap them while the CompactRIO is on, and that'll be no problem. The next question is, both the FPGA and user 1 LEDs are user configurable. So if you look at your CompactRIO, there's a couple of LEDs that are on that controller. So you'll see one labeled FPGA, and you'll see another LED labeled user 1. So what are the differences between these two? So the FPGA LED, that is an LED that you can control in your FPGA VI. The user 1 LED, that one is not accessible by your FPGA. Instead, you would access your user 1 LED through the real-time VI. Now you can describe common RIO platforms. Next, we will configure a Windows FPGA system.